All right. Good morning, everyone. How are you all doing? Good, good? Cool. All right. Does anyone have any questions before we get started? Okay. Sorry, I saw a lot of hand movements, but I didn't know, I was trying to see if it was hand raising or, okay. I think it was just all whatever. Oh, why isn't my Apple Pencil holding a charge? That's a new problem. Okay. Anyone else ever encounter that? No? Okay, all right. I'll have to go talk to IT. Hopefully it lasts through this, otherwise we'll have to move to chalkboard. Or actually, I'll probably switch over to document projector. No, because I won't be able to write. Yeah, it'll have to switch to chalkboard. Well, hopefully it holds out. Okay. All right, so we left off looking at our alcohols. Remember that this whole chapter is, instead of it being mechanism driven, it's now functional group driven. So it is, now let's think about everything we've talked about so far, but let's put it in context of the alcohol. And so the big new thing that we're about to get to is going to be redox, oxidation and reduction, or not in that order, right? It's reduction, oxidation. So the thing that we left off with last class was we talked about that ester hydrolysis. So what was the advantage of doing ester hydrolysis? Oh, okay. Try that again. I just realized you could only see about 1/3 of my screen. I zoomed in, but I didn't zoom in that much. Okay. But do we hopefully have it written down of why ester hydrolysis was the benefit? Yeah. Exactly. It's avoiding E2 because we're using a weak base. How is that? Is that at least everything? Let's see. If that's full screen, and now I'm stuck. Okay, that is the full screen. It's just weirdly offset. But okay, at least we can see everything now. If it does anything wonky and shifts or something, let me know. But yes, so it is avoiding E2. So remember that substitution and elimination are in competition. So if you want to make sure that you exclusively see substitution, that you don't get major and minor, use a molecule that isn't going to be a base so that there isn't any competition. So that was, we did that acetate, use that carboxylate as the really good nucleophile that isn't going to be a base because its conjugate acid is a carboxylic acid, so it was an acid. So it's going to be, if it's a strong acid, the weak base is the conjugate base. So that was a really good nucleophile. So the benefit was we saw exclusively substitution, and then the ester hydrolysis just did it broke it apart. So the whole point was that it was just another way to get to our alcohol, but avoiding that major minor issue. Okay. And then we talked about the mechanism and how the mechanism was going through that addition, elimination, and then acid base, and how we said that it was just you couldn't avoid it because you have a strong base and an acid. And so anytime you see an acid and a base, do acid base. It's very fast. Remember, that was one of our tips when we talked about reactions in general, is that it's kinetically favored. meaning it's going to happen really fast. That's why whenever you see strong acid, I'm like, protonate something, because it's very fast. As soon as you see it, you're going to do it. And we had said that we could have that alkoxide as our leaving group for a myriad of reasons of relative bond strength, stability of products. And we said that the shortcut, the easy way to look at it was, we're in basic conditions. You start with an O-, you can make an O-. And that was our quick trick to remember when we could have that be a leaving group. And that was the only time we will ever see O- as a leaving group. Okay. Do you remember that whole conversation? We're good with that? Okay, cool. So new content, we have addition reactions we will eventually get to. So this is going to be after the next exam. So this is after exam 2 content is going to start with our addition reactions. But I just want to point out that we are going to have ways of making alcohols from addition reactions. So when you're preparing for the final exam, you really want to have a reaction notebook, and you want to be able to say, what are all of the ways I know how to make alcohols? What are all the ways I know how to make acid halides? What are all of the ways that I know how to make a carbonyl? You want that functional group centric summary, because then that's going to make it really easy to do synthesis problems. So I'm including this as a recommendation of like, hey, don't forget when you go to review for the final exam, and it's like, oh, what are all the ways I know how to make alcohols? Don't forget that addition reactions also can make alcohols. Did I talk about the reaction notebook in this class yet? No, okay, that was my other class. Okay, so for the reaction notebook, a reaction notebook can take many different forms. Essentially, all it's meant to do is make you organized. So as long as you are getting organized with your reactions, you're doing the right thing. The classical format for a reaction notebook, if you go into our modules, and I believe I put it under the reference materials. Yeah, you can see Dr. Baldwin's reaction notebook here. So under the reference materials and summary sheets module, you can see Dr. Baldwin's reaction notebook info. And so there's a lot to read there. All of it is useful and helpful. But if you come down to the bottom and you open up the template, this will help you see kind of the idea of how we're trying to get organized. So essentially, you're going to say, all right, what is the reaction name? You're going to put up here. Then you're going to say, what is the general reaction scheme? So that is like that nucleophile plus electrophile goes to your substitution product plus leaving group, right? That's the general reaction scheme. And then you would have your detailed curved arrow mechanism. And then you would include your like different selectivities, so your regioselectivity, your stereochemistry, stereoselectivity, any sort of additional reaction features. And then you would have your reaction coordinate diagram, transition state info, and any sort of example to have it worked through. So if you look at her example, skip over the radical halogenation, because we're not doing that till the very, very end. She did it for an SN2 reaction for you. So the reaction name is bimolecular nucleophilic substitution, or SN2. The general reaction scheme, let me make this full screen. I don't know how the battery went up when it wasn't connected, but whatever. So the general reaction scheme is we're going from like the acid halide to other functional groups. So it's some electrophile plus your nucleophile goes to that substitution, detailed mechanism showing that it's all concerted, and then the summary of like less steric hindrance increases your rate, better leaving group increases your rate, and all of these additional details. So like this is one way of doing a reaction notebook. This is kind of the classical way. This does work for the vast majority of students. So I'm having all of these caveats because I'm working up to the fact that this never worked for me. Like I had to make one. I have a big binder of where I had to do this in grad school for it was graded. So like I had to do it and turn it in for homework. And all it did was kind of create busy work for me because I didn't actually gain anything from it. Like for some reason, it just didn't click well in this format. But the reason I had to do it was because most people did benefit from it. So I will say, if you are the majority, then do this and it will probably work for you. The idea is just to get it all organized, get it all summarized onto a single sheet. And here's SN1 broken down as well, and you can use this as a starting point. So you can now do E2, you can now do E1, and you can do the ester hydrolysis. So you can add each of these into your reaction notebook because it's going to keep building as we add more reactions. Like today, we're going to add a bunch more reactions. So you want to keep everything organized and everything straight. If you try this and you're like, I still am having a really hard time knowing which reaction to do, like it's not really clicking still, then I would recommend doing a different style reaction notebook, which for me worked out to be a list, essentially. So what I did was a couple of different things. So I would do, so there was classical, bless you. So see Dr. Baldwin's example of modules. All right, so Dr. Walter's way is a list. Like it just made more sense for me to not have each reaction on a page, but instead try to put all of the reactions onto one page. And if I could try to do that, then I could start to see the overarching trends. And then it was easier for me to be like, oh, if I see O minus, then I know it's a strong, strong. Like that's where it started clicking for me when I all of a sudden started to discover these trends. So what I would do is a couple of different lists. So I would be like, okay, if I want to make alcohols, I would be like, all right, a product-based or functional group-based list. Or, actually also, what I did was a starting material-based list, which is like, what do I have? So it was two different lists. One was that functional group, it was my target, it was my product, it was what do I want? And then it was all the different ways I know how to make the thing that I want. That was really helpful for retrosynthesis. The starting material one was just what are all the things I know to do with an alcohol? So that was the forward synthesis one. So that helped me a lot with predict the products. So what that kind of looks like is if you're doing a functional group target, it's the whole, what do I want? So if I want an alcohol, then I'm going to say, all right, alcohol is going to be my subsection, and then I'm going to be like, okay, ways I know how to make an alcohol. I know how to do it with a primary leaving group and hydroxide and cold temperatures. So the SN2 is the major. And that was really good with primary. And so then I would like highlight the SN2, and that would be one way. And then I would be like, okay, if I have a tertiary leaving group and water, again, cold, that favored SN1. And that led to my substitution product. And I would add a little note to be like, watch for E2. Watch for E1. And then I would have my ester hydrolysis. So that would be my leaving group. Step 1 is going to be with the acetate. And then I would have, because it's SN2, I would have some sort of aprotic solvent. So I would either, actually, normally, I'll tell you what I actually did. So what I actually did was I would be like, all right, I would just pick whatever was my favorite aprotic solvent. I would just pick one. So because we have a bunch of them, and it's important to know that they're all aprotic so that you know that when I give you one, you can recognize and go, ah, that one's aprotic. But if you're doing a synthesis problem and you have to provide the reagents, it can get overwhelming when you're like, I know 8 of them, which one do I pick? So just have a favorite, have a go-to, have a favorite base, have a favorite non-bulky base, have a favorite bulky base, have a favorite aprotic solvent, have a favorite protic solvent. My favorite protic solvent's water. You know, like just have a go-to so that anytime you need, you're like, oh, SN2 needs aprotic solvent. So what is someone's favorite aprotic solvent? Which is any aprotic solvent you can think of. DMSO, cool, that one's it. That'll now be our favorite. It is totally reasonable because in this case, it doesn't really matter. So I'll add the note to be like aprotic so that I remember that it's aprotic, so that if I saw it on a predict the product one, that I would remember that it didn't have to be DMSO. I didn't have to memorize the DMSO part. It was just that it was an aprotic solvent. It was just something to make it real and complete. And then on step 2, that was where I had that sodium hydroxide in water. That was the actual hydrolysis. So I would get that OH, and then I would add the comment of avoids E2. So then this was how I did my reaction notebook, it was essentially just creating a list of what are all the ways I know how to make that thing. So I'm a very list-oriented person. This is what works really well for me. Some other people prefer what are known as reaction roadmaps, which I don't remember when I bring it in. I think it's next chapter. I show you an example of a reaction roadmap. Reaction roadmaps are what are at the end of every chapter. So if you hate the book, that's fine. They do at the end of every chapter, they do have really useful summaries. So if nothing else, those are good to use. Like just if you're only gonna look at like 2 pages, those are the 2 pages to look at. Look at the end of every chapter because it summarizes every reaction that we're gonna talk about, what are the reagents, and it lists everything in a nice organized place. So that way you're not trying to like start from scratch. You can use the book or you could Google it because there are lots of these that exist online. But reaction roadmaps will be things like where you have so this is essentially option 3. It's basically the same thing as my functional group what do I want list, except that it's circular. So it'll have an arrow pointing from like the bromine, and then you get OH minus and cold, and then you would see that. And then you would have over here like a tertiary bromine and neutral water and cold. And then we would have down here, actually, neither of those would work because they would have to both be secondary. There you go. Sorry. So the point, let me emphasize why that is. So with the reaction roadmap, usually what you'll do is you'll use generic Rs. You won't draw specific molecules. For my list, it was easier for me to draw like the typical substrates that I would see. So seeing the primary, seeing the tertiary, that was easier for me. So that's why I did it that way, because that was my way of like remembering SN2 prefers tertiary, or sorry, SN2 prefers primary because that's the substrate I always drew. And then I didn't have to like memorize as much because I had the example of what is the good one in mind. So then that was my trigger to quickly remember it. And then for SN1 prefers tertiary because that's what I always saw. So I was building up my chemical intuition by just making it repetitive that like, I always saw tertiary doing SN1. So that was like okay, I just need to remember why. The why is because of carbocation stability. But the chemical intuition said, if I see tertiary, I'm doing the stepwise. So the reaction roadmap that I was drawing initially was incorrect because I didn't have the right number of carbons. So usually you would just have like R alcohol, and you would have like R leaving group, R leaving group. So actually, since I'm saying that, I'm sorry to erase something again. Let me actually show you what it typically looks like. So be putting like R groups on, and then you would usually have to have some sort of like qualifier of like, oh, primary is better or whatever. But this is just the like, you're just trying to make it circular to be, here are all the different ways I know how to get to this targeted thing. And so then we would have our 2 steps for the acetate. And the sodium hydroxide. And usually, I will also note, the reaction roadmaps usually only have like, what are the key elements necessary to do it. Reaction roadmaps usually don't have like all of your conditions. They normally don't have solvents. It's normally like, what are just the bare minimum elements to do like a quick identification. All of them are equally good. I just want you to do whatever actually makes it easier for you to see the different syntheses that we have available to us. That way you can start to identify when you want to do one over the other. Because we're gonna, as we keep going through the semester, it's going to become, we have a lot of different ways to make alcohols. So you wanna make sure you know why, or know what they are. The reason why we have a lot of different ways to make alcohols is because alcohols are really useful functional groups. So they are those really good solvents. They're really good weak bases that can easily become strong bases. They're weak acids that could easily become a good leaving group if you protonate them as well. Like the alcohol functional group is just very useful. It also helps make it more polar. It has that really strong polarized bond, not strong bond, weak bond that's highly polarized. So it's just a really useful functional handle. And they are everywhere in nature. It's how we actually get rid of molecules out of our body is predominantly by oxidizing things. We put oxygens on to make it more polar so that then you can pee it out. So like that's how we, as like most living organisms, will actually remove things from our system, is by putting more like OHs and oxygen onto things. Okay. So start a reaction notebook, and I recommend starting it now, so that way it's less overwhelming. Because I repeatedly get told by students that when there's only a couple reactions, they don't feel as much motivation to start, which I get. So then they procrastinate and they wait until right before the exam. But now they're like panicking because they're like, is this like the best way to use my time? And they're like, all right, well, I'll just do it before the final exam. And now they have so many reactions that now they don't know where to start. So then they just don't do it. And then they're like, hey, I'm starting Orgo 2, and how can I best remember all this information? And I was like, oh, do you have your reaction notebook? And they're like, you know, I never made that thing. And I'm like, yeah, I'd still make it now. So start now. It's gonna make your life so much easier. And if you want to do the legit reaction notebook, like the classical form, like I said, does work for the majority of people. That's why I was forced to do it, because normal people benefit from it. I just am not normal, so I didn't benefit from it. So yeah, do it in some way, whatever way helps you. Cool. Do you have any questions about reaction roadmaps? Does that make sense? It's essentially just an organization school technique. Okay, cool. All right, so let's actually talk about this redox that we're talking about. So redox in Gen Chem was that Leo the line goes GR, or oil rig, where its reduction was gaining of electrons, oxidation was loss of electrons, and that is still 100% true. That is a valid statement. It's harder to tell the oxidation state of carbon, though. So for organic chemistry, we have a simpler method so that instead of actually counting and finding the exact number oxidation state, we're just going to look at how many bonds to oxygen does it have. If it has a lot, it's highly oxidized. If it doesn't, then it's not. So our reduction is going to be where we are increasing the number of bonds to hydrogen and/or decreasing the number of bonds to oxygen. So that is reduction. You're either adding more hydrogens or because sometimes it's simultaneous, reducing the number of bonds to oxygen. Oxidation then is increasing the number of bonds to oxygen and/or decreasing the number of bonds to hydrogen. And then the thing to note is just that our carbon-oxygen equivalent bonds are going to be like carbon-nitrogen, carbon-halogen, sulfur, essentially carbon heteroatoms. It's not perfect. And like that's where like if you're calculating the oxidation state, it changes a little bit. But for the sake of just, is it more or less oxidized, you can essentially count any of these heteroatoms as carbon-oxygen equivalent bonds, right? So we get this oxidation ladder. So an oxidation ladder is essentially just looking at the relative oxidation states. So our most reduced or least oxidized is our alkane, our simple saturated hydrocarbon. That is going to be the most reduced. It has the maximum number of hydrogens it can, and so then that is going to be the most reduced. So when we're looking at our hydrocarbons, before we even get into oxygens, this is using that decreasing number of bonds to hydrogen aspect, where your alkene is now more oxidized because it has 2 fewer hydrogens. So that's that decrease in number of bonds to hydrogen aspect. And then your alkyne is even more oxidized because it's taking away another 2 bonds to hydrogen, right? So for the hydrocarbons, that's really looking at the number of bonds to hydrogen definition. And then once you get an oxygen in there, now you've increased your oxidation state even more. So once you can actually have oxygen, that's more oxidized. So if you have 1 bond to oxygen, then you are more oxidized than your hydrocarbons. If you have 2 bonds to oxygen, now you're even more oxidized. So our aldehydes and ketones are going to be more oxidized than our alcohols. Our carboxylic acids and esters now have 3 bonds to oxygen. And to point out the bonds, we're counting every line to the heteroatom, right? So the carbonyl counts as 2. Then that single bond OH, like that counts as the 3rd. So as you are increasing the number of bonds to oxygen, you are increasing your oxidation state. You're becoming more oxidized, right? So that's kind of the easier way to do it for organic compounds, is to look at just the number of bonds to hydrogen, number of bonds to oxygen, and look at that relatively. So we can synthesize our alcohols. So on that, if you're making the list, or if you're doing the reaction roadmap, you would just add these directly underneath the list, or you would add another arrow pointing at the alcohol, because these are additional ways to make your alcohols. If you're doing the classical reaction notebook, you would make a reaction page for each one of these. So it would be putting 4 pages into your reaction notebook, right? So these are going to be ways to make our alcohols via reduction. Because essentially what we're doing is we're just saying, okay, if I want to go that way, if I want to get to the alcohol is my target, then all I have to do is reduce the aldehyde or the ketone, or reduce my carboxylic acid or my ester, and that takes the step down, or down for you, to the alcohol, right? So that's what we're going to look at. So note that our alkenes, the carbon-carbon double bond, are nucleophilic Whereas our carbonyls, those carbon-oxygen double bonds, is electrophilic. But both are going to do addition reactions. So they're both going to be, we're going to lose the pi bond. We're starting with a pi bond, we're going to end with no pi bond. But if it is a non-polar pi bond, meaning both are carbon, same electronegativities, then it starts, the arrow is going to start at the pi bond and go out. For our carbonyls, because it is a polarized pi bond, that carbon is now really electrophilic, which is what we already talked about, right, in our ester hydrolysis. We said that that carbon of the carbonyl is a really good electrophile because we had that resonance structure. I'm seeing a lot of faces that are like, I don't know what you're talking about. So I said that we had this resonance structure so that we see that this carbon is electrophilic because it gets that positive charge. Whether it's a good resonance structure or not, we didn't really talk about. Well, we said that we weren't really going to consider it because all that mattered was that it was polarized and that was making that carbonyl more electrophilic. So that carbon was a lack of electron density, so we're always going to attack it. So whenever you see those carbonyls, the carbon-oxygen double bond, we are attacking the carbon of the carbonyl. So our general reaction mechanism is going to be where you have the nucleophile, which this curved arrow should start at the lone pair, right? So it should start at the lone pair, and then it attacks the carbon of the carbonyl. And because carbon can't have more than 4 bonds, we can't exceed its octet, means I need to have another arrow going away from it. So I need to have my arrow push up onto that oxygen because the oxygen is more electronegative, so it's pulling electron density towards it anyway. So then we're going to push towards that oxygen. That makes a tetrahedral alkoxide intermediate. Essentially, it's tetrahedral, meaning it's sp3 hybridized, right? You now have 4 bonds to carbon. And alkoxide is just telling us you made an O minus, although we won't always make an O minus, but for all of our reactions, we will. In Orgo 2, you're going to talk about the nuances of these. You'll talk about some of the differences between how to draw the different mechanisms. For the sake of our class, we're going to just treat it simply. We're going to do these curved arrows for all of them. So we're going to make it easier for ourselves. So in Orgo 2, you'll have like a more accurate representation. But for now, we'll roll with nucleophile attacks into that carbon, and we get that O minus. And then, so that's our addition step, because you go from pi bond to no pi bond. And then it's just acid-base in order to get it neutral. So you get a tetrahedral alcohol product, meaning it's just sp3 hybridized. It's just, you made an alcohol. We are going to have 4 different reductants that we're going to look at. 2 of them are going to be hydrogen nucleophiles, 2 of them are carbon nucleophiles. They're all going to do the same sort of thing, where these things are the nucleophiles. So we're going to start from there, go to the carbon of the carbonyl, and push the electrons up. We're going to do the same general arrow flow for each of these. For our hydrogen nucleophiles, it's going to be lithium aluminum hydride and sodium borohydride. For our carbon nucleophiles, it's going to be our Grignard and our organolithium. And if you're trying to like panically write that, it's on the next slide, or next page, where it's actually written out and spelled correctly. So our hydride reducing agents are going to be nucleophilic sources of hydrogen. It's important to recognize hydride on its own, like sodium hydride, is a base only. Remember that was one of our strong bases that was not a nucleophile? That NaH on its own is only a base because acid-base reactions happen very quickly and it forms hydrogen gas and then bubbles out. So hydride on its own is going to just take a proton and then vanish, becoming that hydrogen gas. Also note, these will not reduce our carbon-carbon double bonds because the carbon-carbon double bond was nucleophilic. So it's mismatched because these are nucleophiles and that is nucleophilic. So it's not going to reduce the carbon-carbon double bond because I'm adding a nucleophile to a nucleophile. And same charges repel, not attract. So I need to have an electrophile to go with my nucleophilic hydride sources. So my nucleophilic hydride sources are sodium borohydride and lithium aluminum hydride. Sodium borohydride, NaBH4, exists as this ionic state where it is Na+, and then the boron now has 4 bonds. So that boron has a negative charge. Because remember, boron is hypovalent. It normally only wants 3 bonds to be neutral. So now that it has 4, now it's negatively charged. Sodium borohydride is not going to be a good base. The relevance of that is that I'm going to be able to run it in protic solvent. It's not going to react with my solvent. So it's not going to be a base. So I can run it in a protic solvent. And I'm not going to need a workup step. The workup step is that, oh, I need to just add a proton in order to make it neutral. That like acid base that happens at the end, that's your workup step. Why it's called a workup step, I don't know. I've never known. I've always wondered. I've asked lots of people. I've tried Googling it. I don't know. It just is. It seems like one person said it and everyone went, yeah, that's good. And like, I don't know. But that's what it's called. It's called a workup step. And so that workup step is essentially just what it's getting in order to get it neutral so that you can isolate it. So sodium borohydride doesn't need that second step. It is going to have the proton source already in solution, the solvent. So you can quench it if you have excess with dilute acid. It is a weaker reducing agent. So it is not very strong. So the strong one is going to be the lithium aluminum hydride. You can make it stronger with the addition of a Lewis acid. So if you just do normal sodium borohydride in protic solvent, usually it's run in like methanol, ethanol, something like that, then that would just give you your alcohol. If you have a carbonyl that isn't as electrophilic, then you can add a Lewis acid, typically cerium trichloride. So the cerium is acting as that metal, so it's a really good Lewis acid. Remember, both your group 13 and your transition metals are really good Lewis acids. So cerium is up there, I promise. Oh, it's a lanthanide. Thank you. I'm like, I'd never look at the F block. It's number 58. Okay. So yeah, whatever. So it's a part of that like transition metal series. So it's a really good Lewis acid. That was the whole point. So what that does is it's going to react with your oxygen first to pull the electron density farther from that carbon. So essentially, it's going to make that oxygen be positively charged, and it's going to pull the electron density up. And so then it's going to, all it does is activate it more. Don't stress too much about it. Just, if you see that, think of it like a catalyst. Actually, it is a catalyst. It's not going to actually do anything other than make it faster. It's not actually adding any elements. Catalyst. That is known as the LiAlH reduction. The reason that I know that name is because this is one of my favorite reactions. It works so well. So in grad school, when I would get really sad because nothing was ever working, I would then run this reaction and then I would get a 98% yield, and it was like really consistent and beautiful. It was so nice. So if I was like really bummed out, I was like, I'm just gonna make some alcohols today. And I would just do the LiAlH reduction and be like, all right, I can do something. And that was my validating, like, all right, let's try the hard thing again because the easy thing I do still know. That's the main reason why I included it, because it was my crutch for a while. It works really well. It's a really good way of making alcohols. All right. Our stronger reducing agent is going to be our lithium aluminum hydride. It is basic. It is a strong base. It is a very good base. So it must be run in aprotic solvent. It must be run in an aprotic solvent. If you try to run it in a protic solvent, it will do acid-base chemistry and it kills your reagent. You get no reaction. So you need an aprotic solvent you will get none of your desired reactivity. You're not going to react with the carbonyl. You will just do acid-base. You will just deprotonate your protic solvent, and it'll kill your reagent, right? So it must be run in aprotic solvent. Typically, it is run in THF, which is tetrahydrofuran. Tetrahydrofuran, which is this 5-membered ring that contains oxygen. Or it is run in so that is an ether solvent. So it's typically run in that or diethyl ether. So it's usually run in some ethereal solvent. But the main thing is recognizing it must be aprotic. That's a non-negotiable. It usually is THF or diethyl ether. Cool. It must be aprotic. That's the key part of this. In terms of like an actual practical sense, in Orgo lab, do you do an LiAlH reduction? Oh, this usually gets abbreviated LiAlH, sorry. Do you do this reduction? Do you use this reagent? No, is it just Orgo 2? Okay. So it might be just in the Orgo 2 lab. I don't remember. Rochelle salt's pretty expensive. They might not give it to you, but they usually talk about Rochelle salt. All Rochelle salt is potassium sodium tartrate. It is just this really complex chelating agent. Think of it like a good hugger. It is going to hug and just kind of hold on a little extra tight. It's going to hold on to that aluminum metal. So it's really good at soaking up metals because it's going to hug those metals because it loves those metals and it loves to interact with them. It's essentially like a sacrificial oxygen. So it's going to have the aluminum gets rid of our oxygen, gives us back, or actually it's that one. Aluminum will let go of our oxygen if it gets to play with these oxygens. So these oxygens are like, yay, let me hug that aluminum, and it just kind of like holds on to it. And so that is all Rochelle salt is. So it's just a different type of workup instead of a traditional acid-base workup. It's a Rochelle salt workup, which means you just mix it. You just pour some in and then have it wash away all the aluminum. Yeah, just that's what that is if you ever see it. I'm cool with you just doing a normal acid-base workup, right? The idea is this proton has to come from somewhere. Where it comes from is that acid. So these reaction conditions, this hydrogen of the LiAlH is here. It's what's adding to the carbonyl. It's the nucleophile. The hydrogen on the oxygen is going to come from that acid workup. For our sodium borohydride reduction, that's the nucleophile is adding to the carbon. That's where that hydrogen is going. but I didn't need a separate acid workup step because it was the solvent that gave me the hydrogen on the oxygen, right? So this is the big difference, is because this is not a base, it's okay to have something that's slightly acidic in solution. You can have weak acids around. This is a very good base. Lithium aluminum hydride, LaH, is a very good base. So you need to have a protic solvent, which means you got to get the proton from somewhere else. You're going to get it from an acid workup. Cool. So it must be 2 steps. Every time you do LaH, it is a 2-step reaction sequence in order to get to your alcohol, to your neutral alcohol. All right. Any questions about that in general? Like just, we'll talk about like which starting materials you want to match to them, but sodium borohydride is weaker, and that lets you have no workup step. You get to use protic solvent. Lithium aluminum hydride, stronger, strong base, so you need a protic solvent, not protic solvent, and then you need a second step to actually get that proton on your oxygen. All right. So when we look at our mechanisms, the mechanism for that sodium borohydride reduction is going to be, all right, so what is my electrophile between these two? That one, right? The carbonyl. That's the one that gets the partial positive. For all of these, it is the carbonyl. So then what's my nucleophile? The other one, right? The sodium borohydride, the thing with the negative charges. So I need to start my curved arrows at the sodium borohydride, and I need to point towards my electrophile. So I'm going to start at that boron-hydrogen bond, and I'm going to point towards that carbon, right? I'm taking those electrons. Sometimes in lab, or just other textbooks or whatever, they'll sometimes show this as a naked hydride. I would caution you with that because it's not just a naked hydrogen. You have that boron there that's still significant, and I don't want you to mix up the fact that NaH is not like just having that naked hydride. That's base only. That's not going to be a nucleophile. So that's why I'm showing that it's coming from the bond to help emphasize that this isn't just a normal naked H. The boron is there. That's what's making this possible. So then we're going to push our electrons up onto oxygen because carbon can't have more than 4 bonds. And then you get that O minus. That hydrogen is now here. It becomes implicit, but it still exists. So all I did was take the boron-hydrogen bond, broke it, and then drew the line between the carbon and the hydrogen. So the hydrogen still exists. It's just now attached to the carbons and the boron. So then the next step is going to be, all right, I got to get it neutral. So I have that alkoxide, which is a strong base. And so then that is going to get protonated by my acid, my weak acid, but it can take that proton. So that you get this, your neutral alcohol. So now I have that desired product. Where I saw that's where the hydrogen is coming from the methanol from that acidic solvent, the protic solvent. Then what we're going to do is have our oxygen, which is nucleophilic, essentially to prevent it from going backwards so that it's not going to keep taking that hydrogen off and just go back and forth in equilibrium. It's going to have that oxygen attack that boron to form that Lewis acid-base complex. So this was Bronsted acid-base, this is Lewis acid-base. Were there questions? Okay. All right. So technically, you can then have that reagent keep going and react again. So that it has all of these other hydrogens that it can keep doing those same curved arrows over and over and over, and you're just like rinse and repeat, just over and over and over. And it just keeps going until you run out of hydrogens, right? Technically, that is true. What I will say, though, is that every time you make that boron-oxygen bond, that weakens your boron. So now it is less reactive. So every subsequent time that it tries to give up another hydrogen, it becomes a little worse at giving up a hydrogen. So in practice, you will always use it actually in slight excess. You will typically want at least one equivalent. So you want one equivalent in practice. So each NaBH4 donates one hydrogen. That's what the one equivalent is saying, is that I'm only expecting it to give up one hydrogen each time. Technically, and again, in lab, I know they talk about this quite a bit, they will say that you can do 0.25 equivalents of NaBH4 because there are 4 hydrogens. So that will give you a full, like all the hydrogens that you need to go to full reaction. Technically, that is true. In practice, that doesn't happen. In practice, you get like a 30% yield. So if you want those 98s, you want to use 1.2 equivalents, actually. You just want to push it. But yeah, so in practice, because each time you make the oxygen-boron bond, it gets weaker. Right. This is something that, so especially whenever you take lab, normally this is something where students come back to me and they're like, now I'm really confused because I know that I'm teaching it differently than lab does, or even other instructors. And that's just because I've done this a lot. And I can't lie to you about this one for some reason. So I just need you to know that's the case. All right. So that's for our sodium borohydride. For lithium aluminum hydride, our mechanism is still the same. So it's still going to be hydride attacks the carbon, curved arrow pushes the electrons up onto oxygen. You're going to actually see your oxygen couple to your aluminum. So what it actually is that you get that O minus with that ALH3, and that attacks the aluminum. So you actually go that way and then that way. So I kind of skipped a step there. So that is because it's not in a protic solvent. There's nothing else to get that oxygen neutral except for attacking that aluminum. So you're going to see that it will keep reacting, theoretically, again, technically has 4 equivalents. But again, just like with this boron-oxygen bond, each aluminum-oxygen bond is going to weaken the reagent. So it keeps going, 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 until you get here. This is your product of step 1. Or that. I'm cool if you draw this as the product of step 1. Either one. I don't care which one you draw. And then your acid-base reaction, what that does is it just breaks the oxygen-aluminum bond. So then it just separates it to put a proton on hydrogen, and then usually your conjugate base will react with the aluminum. All right, so next class, we'll highlight when you use each one, and then we'll talk about our carbon nucleophiles. Have a wonderful day. Oh, there was an issue with the last homework. Question number 24 had really bad feedback where it kept telling you to do an SN2 reaction when it was actually an SN1. I'm very sorry. I'm reporting it to the publisher, and I gave everyone full credit for it because I know that that like confused people. So you'll get full credit for that question. Have a wonderful day.